Alright, okay, so let's start for today. Okay, I think last lesson, right, we covered a lot of content. So if you're not a fan of that, okay, today is a lot better. Okay, so today, right, in last lesson, perhaps, if we were looking at structure and bonding, some of the ideas in structure and bonding will be applied today. Okay, so we can't just, it's not disconnected entirely. And in atomic structure, we also have a few concepts that we'll discuss today also. Okay, so our focus for today, right, is only on dot and cross diagrams. Yes. Okay, you might ask yourself, dot and cross is a quite easy. Okay, based on secondary school, I personally feel that most people can deal with dot and cross rather easily. But in JC, right, there's a lot of different types of dot and cross diagrams. We're going to look at a lot of scenarios today, and I'll make us practice a lot of different questions because I can tell you guys what's coming up in the next lesson as well. It is called VSEPR theory. Okay, basically, right, if you can't draw a dot and cross diagrams by today, your VSEPR theory next lesson will be a lot more difficult than it already is. Okay, so it's very important for us for the whole of today's lesson to get comfortable with dot and cross diagrams. And not to worry, okay, because we're going to look at some steps and all that, right? I'm pretty sure you guys by the end of the lesson you can do any question. Okay, anyways, okay, let's take a look at some basics first. So I want you guys to turn over to page 19. Right? Okay, so quite a bit of stuff okay, in the first page. Okay, but after that it's all practices. Now, anyways, okay, so on page 19, right? Okay, we look at some preliminary rules first. Now, the first thing that we must always bear in mind is the number 8, right? Now, based in secondary school, we have learned that 8 is the magical number in dot and cross diagrams. You must fulfill the octet rule for all atoms in order to finish up the structure, correct? But today we will learn, right, that 8 isn't as magical of a number as it seems. Okay, there's going to be a lot of exceptions to this rule. Anyways, the second thing we need to determine, what's up? Okay, anyways, the second thing that we need to determine, right, is the central atom. Now, guys, typically, when you are given a structure, you need to determine the center atom, and everything else is also known as the side atoms. Now, this seems very easy from the start, but I want you guys to pay close attention. There are two guiding principles when it comes to determining the central atom. Later on, I will give you guys some wacky examples as well. Okay, usually the atom that can form more bonds. Now, this is very intuitive. The atom that can form more bonds is usually placed in the center. Now, that makes a lot of sense. Okay, so I can give you guys a few examples in a bit. Okay, maybe I'll just look at this first one. Guys, if I were to look at carbon dioxide, who will you place in the center? Now, based on your experiences and based on secondary school, you will tell me carbon. Right? Everyone will tell me carbon. But why is it actually so? Guys, how many bonds does carbon form? Okay, how many bonds does carbon form? Okay, so if you can't remember, okay, carbon can form a total of 4 bonds. On the other hand, oxygen can form how many bonds? 2 bonds, right? Okay, guys, the idea is this. How do I determine the number of bonds so quickly? I'll get to that in a bit. Okay, but if carbon can form more bonds, it only makes sense for him to be in the center. However, there's another guiding principle because this rule alone doesn't encompass all the possible structures. So, the second principle we're going to look at is a bit more tricky. The less electronegative atom is usually placed in the center. Now, what does this mean? Okay, have you seen the term electronegativity before? Maybe you've seen it, but if you haven't, never mind. I'm going to explain roughly what this means first. Okay, now, I'll only touch on electronegativity in the next lesson. Okay, but today's lesson, we just need to know a few basics. Okay, I'll look at the bottom of page 19. Okay, so you can see 2 dogs or 2 cows, I don't know what it is. Okay, so they are playing a game of tug of war, and I need you to imagine, right, that all covalent bonds are basically a game of tug of war. Every single atom in the periodic table, right? So today you might want to take out your periodic table as well. Every single atom has a different amount of strength. Now remember, okay, I hope you all know what tug of war is. Usually the stronger person will pull the rope towards himself, right? The weaker person will lose the rope. Okay, now it's the same idea in terms of covalent bonds. If I were to give you guys this bond over here called CF. Now, in this case, right, everyone always thinks that the bond is right smack in the center. But that's not the case over here because I have two different opponents. And the idea is that fluorine is a stronger opponent. So I want you to think about this. Given that fluorine is stronger, where do you think the electrons in the bond are closer to? Closer to C or closer to F? Imagine a game of tug of war. Okay, they are fighting it out. But fluorine is stronger, so where is the electrons closer towards? F or closer towards? F, right? Okay, so you may be also asking me, how do I know that F is stronger, right? Every single element has a different strength. Now, if I'll give you guys another example, CC. Do you think the electrons in the center in the bond is going to be lying closer towards a certain atom? No, okay, it's both of them have the exact same strength. Imagine you put two people at the same strength, right? The rope is not going to move, agree? So that's what electronegativity is about. In other words, guys, here I need you all to take note of one very important fact that will carry us on throughout chem bonding. Okay, the top three most electronegative atoms are FON. FON. Remember this acronym over here. Basically, guys, fluorine is number one on the leaderboard, followed by number two, oxygen. Third is nitrogen. Why is this enough? Okay, guys, I only talk about three elements, but this is enough, right, for the entire chapter, for the entire dot and cross chapter. Because anything that's not part of FON will definitely be weaker. So we're going to see some examples in a bit. Okay, so I want you all to write down a few examples here. Can I give you guys this compound called F2O? I want you guys to tell me who is in the center. Is it F or is it O? Now this is very obvious, right? Some of you guys will probably tell me O. Because it's very nice for you guys, right, to see oxygen in the middle here, and then just basically you look very symmetrical, very nice, right? Okay, so that's correct. Okay, so why is O in the center? Because guys, who is less electronegative? O or F? O is the basically not as strong as F, right? Okay, so he's in the center. On the other hand, is that the only guiding principle that it fulfills? No. Because I hope you notice as well, apart from oxygen being less electronegative, oxygen can form two bonds. Fluorine, on the other hand, can form how many bonds? Okay, so again, later I'll cover this. But fluorine can only form one bond. So it's very evident, right, that oxygen must be placed in the center. Now, most of the time, guys, the central atom is very intuitive. You guys can take one look and you'll tell me what it is. However, there are some cases, right, later that you will see I'm going to spoil you right now, that requires a little bit of consideration. Okay, let's look at a little bit more examples here. I want you all to take a look at one. Can someone just possibly tell me who is in the center? Is it H or is it O? Okay, based on what you've drawn before, O has to be the center, right? Okay, but why is O in the center? Because O can form how many bonds? Two bonds. Hydrogen can form how many bonds? One. So obviously oxygen must be in the center, right? Now, if you take a look at the second guiding principle, does this make sense? Who is less electronegative, O or H? H. Notice O is top 3, right? H has to be less electronegative. But you notice this is one of those examples where it only follows one of the guiding principles. What I'm trying to say is this: it doesn't always have to fulfill both principles. It's one or the other. You choose which one makes more sense. In this case, for water, hydrogen can never be in the center. Yeah, I repeat one more time. Hydrogen can never be in the center because that doesn't make sense. Okay, so far? Okay, I'll give you guys plenty more examples later. This is just one of many that will come. Okay? Now, with this said, okay, we can immediately proceed to the third idea. Okay, but so far, any questions? Anyone blur about electronegativity? All good, Okay. Now, there's this notion, right, that dot and cross diagrams are full of trial and error. Then you must try again. But guys, I'm going to make it such that to save for yourself time, there's going to be zero trial and error. Okay? And this third point is to help us with that. You must know very well how many valence electrons there are for every single element. And I think you guys know how to determine this. I want you all to clarify, right? This third step is applicable to the side atoms only. Not the central atom, it's for the side atoms. Later we'll just look at some practices. But anyways, if I were to give you guys fluorine, can you guys, okay, and it appears in group 17, right? What does this tell you? How many valence electrons does fluorine have? 7. And guys, having 7 valence electrons means how many bonds do you form? Why 1 bond? Okay, correct. 1 bond is because I'm trying to fulfill the magic number 8, right? So I only need to share 1 bond to receive 1 more electron. I can keep on going. Okay, oxygen is in group 16. So what does this tell you? Okay, we can continue the whole process. Group 16, so it has 6 valence electrons. So how many bonds will you ideally want to form? 2. 2 bonds in order to hit 8 electrons. Okay? Okay, we can keep going. Nitrogen, group 15. So anytime you see nitrogen as a side atom, okay, 5 valence electrons, it will probably form 3 bonds. Okay, last but not least, I think this is where we will stop because we won't go beyond that. Okay, all group 13, 2, and 1 are all metals. Do metals form covalent bonds? No. Okay, so we ignore all of that. Okay, we can just basically stop at carbon, which forms 4 bonds. Now, this knowledge over here will definitely save you a lot of time in exam. Okay, a lot of time later as well. So with that said, I think this is not much understanding involved. I need you all to turn over to the next page. We're going to start with very easy examples first. I want you guys to attempt to draw water, carbon dioxide, and NH3, basically the first 3 examples. Okay, I want you guys to draw whatever you have been taught to draw in secondary school, and then if there's any differences, I'm just going to mention it along the way. Okay, it's going to be slightly different from secondary school, that's all. Right? There's no need to draw circles. You can basically remove that circle and just draw a circle across. Yeah, okay. So the idea is in JC, right? Thankfully, we don't have to draw any circles. If not, your diagram will be a lot more work, it's quite ugly, personally. Okay, no need for circles. Correct. No, IP doesn't teach you this. Yeah, okay, O levels does. Some of you guys have your own notation. I'm going to maybe fix a little bit of that. So don't go beyond your part 3. Okay, I need to fix all the small little things that are not wrong, but in JC there's a preferred manner, right? I'll go here. Oh yeah, you don't need to lost it. You may find it in the library. Oh. Or like everyone else. Everyone else got sick. Yeah, so now that's over. Interesting example. Okay. I'm just going to talk about a few things right now. Okay, so you don't actually need to tell me who is the dot and who's the cross. Because if you only use 2 notations, basically a dot and a cross, you will just have to alternate between the atoms. So it's self-explanatory. You can save yourself some time. Okay, and some ideas over here, I think there's no problems. Okay, these are just for me to tell you guys how we can draw all this. Okay, so the first one, oxygen is in the center. How many bonds do the side atoms form? Hydrogen can only form 1 bond. So immediately just draw 1 bond. Okay, this is where, right? Okay, some of you guys like to do this, but I will prefer if you draw it horizontally. Now, it's not that you are wrong, you're still correct. Okay, but the idea is that when you convert this into the actual structure, right, usually bonds are horizontal, right? So we try to maintain that horizontal integrity as well. Okay, and you can take a look at the central atom. Are we finished with the structure? No. Okay, so remember, oxygen has a total of 6 valence. 2 of which were used in bonding. So 4 of which are not used in bonding. You all know what these 4 electrons are called? Okay. Electrons that are not used in bonding are called lone pairs. Right? So bear in mind the idea. This is called a bond pair. A bond pair is something that's involved in bonding. A lone pair isn't. That's it. Yes or no. Alright? Okay, so I recommend you guys to start using this idea instead. Okay, I will show the reason why this gets a little bit more of a bigger problem is when you all look at carbon dioxide. Okay, carbon dioxide is quite straightforward because oxygen on both ends. Now, oxygen can form 2 bonds, right? Now, when you all draw 2 bonds, I sometimes still see you guys try to use this, but I don't recommend it because it's hard to troubleshoot when we look at bigger, harder structures later. Now, reason behind that is because your double bond, right, we should stick to horizontal notation. A bond is a dot and a cross, so it's horizontal. Okay, we try to maintain this idea, right, for the rest. Okay, it must be consistent. I see some of your answers. Okay, one of them is different from the other, so the notation must be consistent as well. Okay, so we have a double bond each. Anything else that we need to fill up? Oxygens have lone pairs, right? Okay, so 2 lone pairs, basically 4 electrons. Anything else we need to fill in the center? Okay, no more, right? Okay, because carbon has 4 valence and you have drawn all 4 crosses. Perfect. Finally, we have NH3. Okay, so NH3 looks something like this, where you obviously must surround nitrogen with the H's. How many bonds can the H's form? Hydrogen can form 3 bonds, right? Okay, 1 each basically. Okay, so 1 each. And then afterwards, nitrogen in the middle. Anything else? Okay, so 2 more as 1 lone pair. Okay, so at the moment, these 3 you will draw right now and you'll never draw again because these are too easy. Okay, you will never see them ever again, right? Okay, so anyways, these 3 examples are just to make sure you guys are on the same page first. And with that said, I want you guys to try the next 3 examples. Okay. And in the next 3 examples, there's one of them that's particularly more difficult than the other. Right, give it a try. Okay. All I have to say is by following whatever steps that I told you all just now, you should be able to come up with a structure for a difficult question, which I'm sure you all can see with that. Okay. Okay, so I hope you all figured out, but that O3 is a difficult one. Right? I want to see what you guys think about it. Right? Try a few iterations. Okay. If you're not too sure, you can just skip to the last one first and come back to it. Okay, I see both of you try to draw a triangular formation. Okay, so that's a common answer that I usually get. Okay, this is not correct. Okay, so there's no such thing as a triangular formation like this. No worries. Okay, it's not that difficult. You just have to surround the oxygen with two more oxygens. That's it. So you can just draw a straight line like that. Yeah, and that's good. You can get the correct answer from this. No worries. You might have spotted some errors in your structure, but no worries, because there's something additional you need to do over here. That's why I suggest just draw whatever you can first. Okay, then you can move on to the last part. Because clearly O3 is a little bit different. I want to see what we can come up with to fix whatever problems that you might have. Something special. There's something special here, yes. Something special. Yes, in O3. You can try it. I don't know. I'm just going to draw CH4 inside very quickly. Okay, I want you guys to try BF3 and then we will come back to ozone together. Oh, 4 dots. Okay, you must use dot and cross. Yeah, okay, because I am aware that all of them are oxygens, right? I know you're thinking all of them are the same atom, so you use only one rotation. But no, okay, so the idea is that, right, you must alternate 3 times. Doesn't matter whether they're the same atom or not. Okay, so what if you use dot for this guy must be cross, and then you're back to dot. Or cross, dot, cross. Yeah, it has to alternate. Doesn't matter what kind of atoms they are. Alright. I want you guys to try your PF3 first before I talk about ozone. Right. Okay, I'll move on over to your PF3. So it's quite simple. Okay, PF3, right? The central atom check again. Make sure you guys locate boron correctly in the periodic table. PF3 also a little bit special, actually, now that I think about it. Okay, so you guys have had your own fair share of experimenting with these structures. I want to talk about BF3 first. Okay, because you guys may have encountered one small issue with BF3 as well. Okay, once again, B must be in the center. Okay, because boron has to be less electronegative than fluorine. Fluorine is like the most electronegative. Okay, and because of that, guys, how many bonds can fluorine form? Okay, 1 because 7 valence electrons, right? 1, 2, 3, 4, 5, 6, 7, 1 bond. 1 bond, 1 bond. Just make sure you fill in all the lone pairs. He has 6 lone pairs because only 1 out of the 7 electrons are involved in bonding. So that was fine so far. But now, right, guys, okay, the central atom, I see some of you guys doing this. Now, by doing this, right, guys, I think you are trying to fulfill the 8 valence electron rule. I know. However, how many valence electrons does boron have? Okay, where is he in the periodic table? Okay, boron is in group 13, so how many valence does he have? 3. Now, guys, if you have 3 valence electrons, you cannot suddenly give me another 2 crosses over here. Okay, doesn't make sense. In fact, this right here is the final answer. 3 valence electrons, and each of them form a bond each. But guys, what's something weird about this compound? What's something special about this? You all notice? How many valence electrons does the central atom now have? 6. which is a little bit odd, right? Because usually we say that 8 valence electrons is the mass. As mentioned today, there are times where you will not fulfill 8 valence electrons. Today we will cover all the possibilities. So take note, guys. Because boron has only 3 valence electrons, it can only form 6 electrons in total after forming 3 bonds. Unfortunately, that's the case, and we have to leave it as such. Okay? So this is one of the special cases that I'll bring back later on. But now, for the moment of truth, okay, let's take a look at O3. O3 is also known as ozone. So this is a commonly tested molecule because it's there's a bit of real life application. You all know the ozone layer and all that stuff. Okay, so just pay attention to this. High chance they will test. Okay, so guys, please start it. When they test dot and cross diagrams, they will not test you pretty much more than 1 or 2. Okay, so they'll give you hard ones. They won't bother with the rest. Okay, now oxygen is in the center, obviously, because who else? Guys, can I ask you all, the side atoms, how many bonds can each of them form? As far as I thought, you 2 bonds, right? Now 2 bonds, let's just stick to it. Okay, let's just draw a double bond for each, and let's just fill all the valence electrons on the side atoms. So as of now, all the side atoms have 8 valence electrons. And you look at the central atom. Is there anything else that I need to touch up on? Oxygen must have 6 valence, so it must still be there. It's just not doing anything, right? Not involved in bonding. So is this the answer? What's something weird about this? As you guys have noticed, there's more than 8 valence electrons, that's the problem, right? And we cannot hold more than 8 valence electrons. That's not possible for oxygen. So guys, that's what I'm going to introduce right now. Okay, there's a 4th thing I need you all to take note of. It's not exactly written in the notes, okay, because I'm kind of rephrasing it a little bit. Okay, if the central atom cannot hold more than 8 valence electrons, this is what you need to do. You will encounter this quite a lot later on. So if they cannot hold more than 8 valence electrons, you guys need to resort to dative bonding. We have learned dative bonding in the previous lesson. It is a type of covalent bond. Now we're going to incorporate that into our structures. Okay, and just to make your life a little bit easier, right? Dative bonding, when you do for dot and cross, is always from the central atom giving electrons to the side atom. It's never the other way around. It's not side give to center. No, center give to side. Okay, I realized they never taught me this in school. It's only after years of realizing and doing dot and cross diagrams. Then I finally realized that there's only one scenario. So I tell you guys this now so that you never ever have to think about it again. So guys, we come back to the structure, right? We need to resort to dative bonds. So perhaps now 2 bonds and 2 bonds is a little bit too much, right? Can I just erase one of the bonds? Now guys, I mentioned about dative bonding, but some of you guys, while doing, right, you have resorted to another solution. So let me explore that first, guys. Just now, 2 bonds is too much, so what will you try logically? Single bond. Okay, come, let's try a single bond, see whether possible first. Single bond means like this. How many electrons do I need to fill up on oxygen? 5 more. 1, 2, 3, 4, 5. It's a bit weird, right? How can an electron be there alone? Furthermore, you see the middle electron, the middle oxygen, 1, 2, 3, 4, 5, 6. It also has a singular electron over there, which is not possible. You have not learned this before. Right? So single bonds clearly do not work. And furthermore, this 2, 4, 6, 8, 9 electrons, definitely not possible. So we have to eliminate the possibility of a single bond. Double bond didn't work, single bond didn't work, let alone a triple bond. So that's why we can only explore dative bonding. How does this work? Okay guys, you look at the oxygen in the center. How many more electrons do I need to draw? 2 more, because 2 more in the center, right? I have to give it to the side. So in your diagram, I need to see 2 crosses or 2 dots, depending on which one you're at. Remember, guys, it's all about alternating your notation. I don't care whether they're the same atom or not. They have to be dot and then cross, or cross and then dot. Then how do I fill up the rest of the electrons on oxygen? What do I do? Anything else to fill up? Oxygen has 6 valence electrons itself, right? But it did not. None of them were involved in bonding. It only took in 2 electrons for free from the oxygen in the center. Can you see that? In other words, guys, does this work? Can we fulfill octet? Take a look. It fulfills octet, right? This oxygen here has 6 plus 2 have 8 already. Oxygen in the center have 2, 4, 6, 8 also. Same as the guy on the left. So this right here is your answer. So I've introduced a fourth rule. Now you shouldn't have any issues with this because I've told you all about accurate. Okay. Very, very important question. High chance of testing. So just make sure you take note of this. Okay, and that's just barely scraping the tip of the iceberg. We have a lot more to come. All right. Any questions so far? No? All right, I'm going to erase some of the easy ones. Let's explore more types of molecules. Okay. Okay, so you can pretty much move on to the next page already. So guys, let me tell you all how to draw this structure. How can we draw all these structures over here? Now what are they? Now you can see a charge, right, evidently. So they are all ions. Now the idea is that nowadays, guys, you will never see the ions that you draw as like Cl minus or O2 minus. These are out because they are known as monoatomic, one atom. But now we're going to look at polyatomic atoms, polyatomic ions, sorry. Okay, so how does this work? Let's look at two rules. Ions only have two charges to consider. Guys, when you see a plus charge, what will you do? Do you give an extra electron or do you remove an electron? Plus charge, cation. Cation must have less electrons, right? So you must remove an electron. Okay, that's very logical. When there's a negative charge, that means you have extra electrons. You add an electron. However, we have multiple atoms to consider. It's not just a singular atom. So the question is now this. I'm going to give you guys a fill in the blank scenario. Do you remove an electron from the more electronegative atom or the less electronegative atom? Same goes for add. Do you add to the more or less electronegative atom? Want to give the first one a try? Make a guess. I could just tell you guys to memorize for the notes because everything is there. But I need you to understand the logic why. Now, you think about it, guys. Electronegativity is basically tug of war. Every single element has a different strength, has a different power, right? Do you think it's easier to remove an electron from a very strong person or a very weak person? Weak. Logical sense, right? Okay, so you must remove an electron from the less electronegative. On the other hand, guys, if you were to give an electron up for grabs, who would snatch it first, the stronger person or the weaker person? Stronger person, right? So you add an electron to the more electronegative atom. Once again, I never tell you guys all the different electronegativities. You just need to know that that will cover most of the thing. So guys, I want you to try the first question. NH4 plus. I want to see how you guys manage to get the structure for this. Okay, and then I'll do. Okay, so turn over to the next page. More examples, a lot of different ions for us to explore. Right? So give it a try. With whatever that I've said so far, right, you can definitely get the structure. Right? This one. I draw Na4, but I don't see a plus charge. Okay, so I need you all to do something like this. Okay, you need to draw a bracket surrounding the entire structure like this. Okay, and now let's see how to draw this structure. Alright, see whether you want to plot it. Right, the plus charge means you must remove an electron, but from who? That's the question. Who do you remove it from? Hydrogen. Okay, because nitrogen is one of the top three, so you cannot remove from helium. So I'm going to remove from this unlucky hydrogen on the right hand side. Doesn't matter, I'm going to choose this guy. How many electrons does this guy have now? None. That's very weird, right? This guy is now eliminated. Okay, never mind. How about the other three hydrogens? How many bonds can they form? They all still have their one electron, so just draw the single bond for all three of these guys. But for some reason, guys, we still need to fit this guy into the structure. He can't just be floating in the middle of the nowhere. How? Exactly, guys. You'll notice, right? Okay, it's very natural because nitrogen has 5 valence electrons, 3 of which are already used in bonding, and hydrogen turned up without an electron. So this guy is like, okay, you know what? I'll be a bit more generous. I'm just going to give you my 2 electrons to share. So that's how this is being done. Any questions? Okay, so dative bonding, guys, do not just be too rigid on this idea. Okay, I know the central atom doesn't hold more than 8. Okay, but sometimes it calls for dative bonds. Okay, there's no rule for this because this is very natural. Okay, I'm sure some of you guys got it also. Okay, let's try the rest. Right, okay, so I want to try perhaps the next 2 more first. Okay, then I'll cover it. CO3 2 minus and NO3 minus. And you also notice, right, because last time secondary school never teach you guys dative bonding, you can't draw so many structures. The moment this dative bond comes out, you can pretty much draw everything. Right? And remember, you need to deal with the charge first, basically. If you don't deal with the charge, nothing will be correct. Okay? You guys have looked at CO3 2 minus. Okay, let's give it a try also. Okay, at this point, I'm sure you all noticed, right? The central atom is quite easily determined. Okay, but now we have a 2 minus charge. Okay, we talk about plus charge plus 1. Okay, but how about 2 minus? Okay, again, the minus charge means you must add an electron to who? Okay, which is oxygen, right? Okay, oxygen is more electronegative than carbon. Okay, but I give you two options. Do you add two electrons to one oxygen or split the two electrons evenly across two oxygens? Which option, the first or the second? Okay, so based on the notes, right? Okay, they also told you guys, but you must split the electrons evenly across two oxygens. Meaning to say,
Really giving your students more test, right?
yeah,
You have more test.
yeah, it's really the value. Okay, so anyways, oxygen now has how many valence, guys? How many do they have each? Okay, initially they have 6, right? But then they get one more, which is 7. 7 electrons can form how many bonds? You just need to form one bond. So that's the idea here. So this still works. Okay. Oxygen here has 7 electrons. You're gonna form a bond. Just like this guy as well. Also 7 electrons form a single bond. Any issues here? So it's always counting the number of valence for the side atoms. Not change that. Okay, now that it's just an atom, it's just an ion only. How about the oxygen on the left? How many electrons does he have? He has 6 valence electrons, correct? So 6 electrons means you can form 2 bonds. We try that first. So 2 bonds like this, fill up all the other valence. Is there anything else I need to fill in the center? Hey, look carefully. Carbon has 4 valence and all 4 crosses are involved in bonding. That's it. 2, 4, 6, 8. So it doesn't exceed 8 electrons as well. That's the answer. No dative bonding involved. Nothing special involved. It's just a double bond and 2 single bonds finished.
So when you make an electron to more
yes.
You mean that electron is not coming from the carbon?
No. Okay, guys. This electron comes from elsewhere. What does elsewhere mean? Guys, you understand, right? That an anion cannot just exist as an anion. We have something like sodium carbonate, right? The 2 electrons come from 2 sodium. Does that make sense? So right now, we can just assume it doesn't matter where it comes from, but it just comes from elsewhere, not from carbon. We are adding these electrons yourself. Feel free to give them free electrons. Okay. Similarly, when you look at the cation, you are removing this 1 electron. You know where it goes to? Fly away. It must go to an anion. Right? Yeah, that's the idea. For all you know, these 2 electrons that you are adding are coming from 2NH4+, also possible. Ammonium carbonate. It exists as well. Okay, so just don't add from carbon alone. That doesn't. Yeah. It's additional new electrons. Okay, give NO3 minus a try also. Okay, at this point, I think you guys can figure out all the other scenarios already. So you can try the rest. Right, after NO3 minus is ClO minus and SF3 plus. Should be able to deal with all this. Or to write some answers on the board. Okay, NO3 minus is on the board. That is one dative bond, one single bond, one double bond. Then we have ClO minus. Okay, so the less electronegative atom is, okay, let's look at this example. Okay, so you see a plus, so you must remove an electron. Okay, do you not know, like, why do you remove from the less and not the more? Is that what you're asking? Or you don't know what this means?
So I don't recall what we have to do.
Okay, so you notice over here, right? Okay, let's just restart Na4 plus. When you position all your atoms ready, you must settle the charge first. Basically, to deal with the plus charge, you remove an electron from the less electronegative atom. In this case, who is less electronegative? H or N. There's only two, right? H. So for this H, I'm going to remove his electron, 1. So hydrogen now has 0 electrons. That's how for the rest of them, they're still normal, so they all still have their single bond. But here, to accommodate the last hydrogen, he cannot contribute anything, so it is a bond. So it's quite similar to the idea in part 5. Okay, so let's talk about part 5. Sn3 plus. The plus is to remove an electron from the less electronegative atom, which is sulfur. Yes. So sulfur initially has how many valence? 6. Now it has 5. Okay, just bear in mind the 5 first, because fluorine can form how many bonds? Or view the side. Fluorine is a single bond, so just draw a single bond for all the fluorines. So something like this. Can you see that? But you notice sulfur must have 5, right? You notice I've only drawn 3 in bonding, so the other 2 is just a go back. That's the answer.
That's it.
Yeah, that's the answer.
Oh, that's the thing of my book. You guys are.
Oh, you know that. That's it. Yeah. Okay. So last but not least, you have ClO minus. The minus means you add an electron to who? Minus you add to oxygen, right? Okay, so you notice, right? There are some compounds where there's no center. Okay, so there's no such thing as center nor side atoms, but doesn't matter. Okay, your oxygen has 7 valence, which means you're forced to only have 1 bond. Then you just fill out the rest, see whether this makes sense. Chlorine has 7 valence, so lone pairs. So this actually makes sense over here in this context. So when there are cases where there are only 2 atoms, right? There's no center, it is okay. You just need to fulfill whatever you've been taught so far, right? It usually leads you to the answer. Any issues so far? Okay. Alright, okay, very good. So these are just ions. They're going to be practicing more ions with a special twist to it also. Okay, but before we flip over to the next page, right? I want you guys, if there's a little bit of space, I want you all to try to draw 2 structures for me. Okay, just try to draw these 2 structures. Again, just based off whatever that I've taught you guys, you definitely can draw these structures. Or maybe one of them. Yeah, at least. Might encounter some problems for NO2, no worries. Okay, there's a reason why I'm asking you guys to draw this because it's a good transition to the next segment, right? There will be issues with NO2 because I haven't taught you a new idea yet. But SO2, I expect you guys to be able to draw. Okay. If you feel a bit stuck with NO2, no worries. Okay. It's meant to be stuck. So you can go over to SO. New idea. Yes. There might be a David bond inside the one, depending on how you guys draw it. Oh, your artists, yes. Cricket gang. If you've seen them at school before, you might know how this might be. Yeah. Let's go over the answer here. Right. I talk about SO2 first, then I talk about NO2 because SO2 I expect you guys to be able to come up with a structure. Alright. So SO2, so this is your thought process, follow through it as well. Oxygen can form how many bonds? 2 bonds, right? Okay, so 2 bonds each, and then you fill up everything else like that. How about sulfur in the middle? How many more electrons do I need to fill up? Okay. Sulfur has 6 valence electrons, so I need to draw another 2 crosses, agreed? Okay, so what's the problem with this structure? Oh, whoops, actually there's no problem, this is the answer. Okay, so what's going on over here? Sulfur has 10 valence electrons. Am I tripping? No, I'm not tripping. Okay, so this is actually the correct structure of SO2. Okay, later we will just include this in our practices. This is correct. What you guys would have done is this. Oh, there are more than 8 valence, so let me erase a double bond. And what will you have done instead? You guys would have given the last 2 electrons as a negative bond to oxygen, correct? Now you will see that it makes sense too, right? Oxygen has 8 electrons, sulfur has 8, oxygen also has 8. Then why is this wrong? Okay, why is this wrong? Okay, because I will talk about this again later. The idea is that, guys, 8 valence electrons is not as magical of a number as it seems. There are elements that can hold more than 8 valence electrons. I'll come back to that idea later on. You might be asking me, then when do you change it to a negative bond? When do you leave your answer? Okay, I'll come back to that later. Okay, so let's come back to SO2 in a bit. But right now, let's settle another scenario, which is Okay, so one scenario we're going to cover is you can hold more than 8 valence. The other scenario is NO2. What was the problem that you guys encountered with this? Can you tell me? Okay, what are some problems that you all have encountered? What's so weird? How come nitrogen got one remaining electron? Now what do I mean? Oxygen has a double bond, so I'm just going to fill in the double bond as seen over here. Correct so far? But nitrogen has 5 valence. I only have 4 dots. There's a 5th dot over there just sitting alone. Now, based on what I told you guys just now, I told you all that this is not allowed. However, this is now allowed because if you all remember, right? Okay, there was like a singular electron like this, right? Okay, so yeah, this is a new concept which is explained on the next page. So you all can turn over to the next page. I think it's point number 2. So on point number 2, this is what has been mentioned. We're going to introduce the idea of a radical. What on earth is a radical? Okay, I want to highlight the keywords. Sorry, highlight the definition because the definition will be tested. A radical is a species with an unknown with an unpaired electron. In other words, a radical is a species where you can have one singular electron without a partner. But when does this happen? It doesn't happen every time. It only happens if there are an odd number of valence electrons in the compound. It makes sense because you can think of it as your class. If let's say your class is made up of 31 students, and your teacher asks you guys to do pair work, there's always that one same person, right, without friends, right? Okay, so that guy doesn't have partner. It's the same idea here. If you look at NO2, can someone tell me how many valence electrons this guy has? A nitrogen has 5 plus 6 plus 6. Not the total number of electrons, but just the valence. Okay, because we're only doing valence in the bonding. Okay, in other words, guys, this guy you notice has 7 valence electrons, which is an odd number, so this lone electron is allowed. I don't expect you guys to know from the get-go. I don't expect you guys to go and count the number of valence electrons for every single question from now on. I need you all to just do whatever you do first, and then you just realize, hey, is it possible for me to have a singular electron here? How do you verify? You verify by counting this total. That's what you should be doing instead. Does that make sense? In other words, guys, okay, if you want to take a guess, okay, where should the lone electron be? Let's just say you never draw anything. Where should the singular lonely electron to be? Between your N or O? Where should it be? Okay, so guys, it only makes sense for it to be on N, right? Which it actually is, because nitrogen is the odd number. So I want you all to try another example, which I don't think is in the notes. Okay, so you can write down on this page also. Another species I'm able to try to draw is CLO. Now you notice I'm going beyond the notes, because I feel that these examples are starting to see more often as well. Okay, so we settle this idea of radicals first. Later we come back to the other example. Alright? Hello. Okay, just copy this example down and preferably on page 24 under the radical section. Okay, so you guys have tried already. Now, CLO, right? Okay, maybe it's a spoiler. You guys know it's a radical. Okay, but what if you don't know? You go into the exam and then you sit down and you see this. Okay, same thing, guys. Usually, I don't tell you guys to count the electrons from the get-go. It's not feasible to do that every time. Okay, over here, CLO, I need you guys to go and just do whatever you can first. But then there's another problem. I don't have a central atom nor a side atom, right? So what can you try first? Okay, so the idea is that you all see oxygen, right? You might tell yourself, okay, there's a double bond. Okay, so let's try that. Okay, oxygen with a double bond here. Looks like this. How about chlorine? Anything else to fill in? I have remaining 5, and you know 5 is an odd number, right? So 1, 2, 3, 4, 5. Okay? So, if you can see this, guys, is this correct? Is there anything wrong with this? Okay, you will notice that chlorine has 5, 6, 7, 8, 9 electrons. Is that possible? It's actually possible here. Because I did mention the next thing that I want to cover is an expansion of that. there are elements that can hold more than 8 valence electrons. And we will revise our rule later. So number 4, we put a star next to it for now. There is a revision of that rule in a bit. Okay? So ClO, this is how the radical is like. Sometimes, right, they might print the radical on chlorine. How do we know that? Because chlorine has 7 valence, oxygen has 6. 13 is an odd number, so we know there is a lone electron that's allowed. Okay, they will print sometimes with a dot on top of chlorine also. They never print over here because why would they spoil it for you guys? Okay, anyways, any questions so far? Okay, so this is the correct answer. I'll come back to this again. I know you guys might be a bit confused about the idea of more than 8. Never mind. Okay, we'll come back to it again. Okay, so guys, let's take a look at this idea of expansion of octet. Now, this one I need to explain how it actually works. Okay, so yeah, how does this work? Who can expand the octet? That's our most burning question at this point in time. Guys, let's write this down. Okay, who is your period 3 elements and below? Now, guys, I just have to be very clear about this. Okay, what does below mean? Does it mean period 2, period 1, or does it mean period 4, 5, 6, 7? Any guesses? Okay, when they say below, guys, they physically mean below. So if you look at the periodic table, what's below period 3? Literally, it means 4, 5, 6, 7. In other words, guys, you all notice only period 1 and 2 must hold 8 valence electrons. In other words, it's quite mind-blowing when I found this out as well. The majority of the elements can actually hold more than 8. So this 8 valence electron octet rule isn't as good as it looks already. Only a minority, only period 1 and 2 cannot expand its octet. Now then the question is why? Sometimes they ask why, and I need you guys to write down this phrase again. Yeah, I know it's already in the notes. I know everything is in the notes. Okay, but no point. Okay, you need to write it down. The reason is because period 3 elements and below have energetically accessible vacant orbitals. Okay, so orbitals, keyword that we learned in atomic structure. It's coming back. Highlight a couple of words. Vacant is a very important word. Later I'll explain what energetically accessible means. Everything here will make sense. Okay? There's a page, okay, next page, right? Okay, it explains everything as well. Okay, but this one, right, guys, don't need to read now. Okay, a lot of the things in the notes is for you guys to go back and read yourself in case you forget what I say. Okay, so just take a look at what I have over here. How does expansion of octet work? Okay, first of all, guys, what is energetically accessible? Now, in atomic structure, I drew this diagram. This is an energy level diagram where we can detail all the orbitals. 1s, 2s, 2p, so on and so forth, right? Okay, do you all remember what's the lowest energy level? 1s. Okay, good. 1s is the lowest energy level because it's the closest to the nucleus, right? Okay, it's like super close, very, very close to the. Okay, so anyways, okay, what's next? After 1s. 2s. Now, guys, from 1s to 2s, is there a very huge jump in energy level or minimal jump? Okay, perhaps I'll give you guys an example to help illustrate this. Okay, to understand period 3 and below, right, I'm going to draw a period 2 element and a period 3 element, which is phosphorus. Okay, let's write out its configuration. Nitrogen is 1s2 followed by, okay, we can all do 2s2 and then 2p3. Okay, how about phosphorus? 1s2, 2s2, then 2p. 6 after that, 3s2 and 3p3. Okay, total 15. Okay, guys, I just want you all to pay attention to the valence shell. So, what's the valence shell in nitrogen? Remember I think we need to recap a little bit of this. Remember the hierarchy. Okay, the largest is quantum shell followed by subshell, and finally, the smallest unit is orbital. The orbital is something that can hold how many electrons? 2 electrons. Okay, now let's take a look. Now, looking at this, okay, we are interested in the valence shell. When I say valence shell, I use it very what are we actually doing? The quantum shell, the outermost quantum shell, right? So quantum shell here is who actually? Remember, quantum shell is represented using numbers. In other words, I'm only interested in the second shell. How about for phosphorus? Okay, the third shell, good. Okay, so I need you to write this out and then underline your second quantum shell and your third quantum shell, respectively. Okay? Now let me erase this. Okay, you have to remember all these ideas again. Okay, no worries, I think your school is going through this again, so you have a second round of looking at this chapter. Okay, anyways. 1s, then 2s. Guys, the energy jump should be very high or very low? Okay, you're jumping a quantum shell, right? And quantum shell was the largest unit. In other words, there has to be a very, very high jump. But then from 2s to 2p, is the jump very high? Because what jump is this? Is it a quantum shell jump? It is only a subshell jump. Okay, subshell use SPPF1. Alright, okay, so I need to see a very minimal jump over here. So in the atomic structure lesson, I drew this out. You can draw this out again. Okay, why not? Okay, so you are possibly gonna be asked to draw this in future. Okay, then from 2p, what's next? Which is very minimal or very high, very large jump, followed by 3p. Okay, so 3s to 3p, very minimal jump. And guys, after 3p is actually what? I know it's not mentioned over here in the examples, but after 3p is. Remember. Okay, after 3p is technically 4s, right? But that's actually 3p as well. And let's look at the idea here. If you look at my diagram, my levels are very close to each other. Reason behind that is because they are very energetically accessible, which means the energy levels are very, very similar to each other. Okay, does that make sense? Now, if the energy levels are similar to each other, what does this mean? Okay, we come back to this. But let's look at nitrogen first. I want you guys to take a look at the electron in box diagram for nitrogen. Okay, how many boxes do I draw for 2s? Okay, just one box, right? Because what does a box represent? A box represents an orbital. Okay, so 2s2, so I just got 2 electrons here. How many boxes do I draw for 2p? 3 boxes because P has 3 orbitals. How do I arrange 3 orbitals again? Okay, one each. They have to be single first before they are paired up. Does that make sense? Okay. Now the idea is this, guys. I want you all to see how many unpaired electrons are there in nitrogen. Okay, good. I have 3 unpaired electrons. So logically speaking, how many bonds can I form? 3 bonds as well. Make sense? You just need to form a bond here, and a bond here. So the number of unpaired electrons, this is what we learned in atomic structure. It's not exactly just how many valence electrons you have in total. It's about the number of unpaired electrons. Having 3 unpaired means you can form 2 bonds. But now let's explore a period 3 element. I'm going to draw 3s. Okay. 3s is basically 3s2, same as before. 3p is also 3p3. See that? But guys, because 3d is very, very close in energy to p, we can also take 3d into consideration. But for phosphorus, is 3d occupied by anything? No, it is vacant because there's no 3 needed at the moment, right? But it still exists because you are entering the third quantum shell. The third quantum shell has a d subshell containing 5 orbitals. Does that make sense? It's just empty at the moment. I don't want you guys to think that it doesn't exist. It's there. It's just not used. Makes sense. Okay? Anyways, guys, it's just empty storage. Now look at this currently. Currently, phosphorus can form how many bonds? How many unpaired electrons are there in phosphorus? 3, right? So you can form 3 bonds, and that's possible, that's correct. But guys, can it form more than 3 bonds? Answer is yes. Why? Here, remember, electrons, do they like to be paired with each other? No, they will face a lot of interelectronic repulsions. But can he escape? Basically, imagine you don't want to share your room with your sibling. You want to move out to another room. If there's another room in your house, right? Do I have other rooms to spare? Yes. I don't like sharing room with my brother. I share room with my brother until now. I don't like it. Okay, but unfortunately, my house is too small for having my own room. So I have no choice. I'm basically connected. I don't have additional storage for me to move out. So this guy is only limited to forming bonds. However, phosphorus is like living in the bungalow, right? This guy, he doesn't want to sleep, that's completely fine. He can move into another room by himself. So guys, taking a look at this, how many unpaired electrons are there now? I have 5 unpaired electrons, meaning to say, how many bonds can I form? 5 bonds. And if you can form 5 bonds, how many electrons can phosphorus hold maximum? How many electrons are there in one bond? 2, right? So 5 bonds is 10 electrons. Okay, phosphorus can hold a maximum of 10 electrons because of this idea. Does this make sense? Okay, so he can choose to expand his octet if it's required to. If not, he can just fulfill 8 valence, that's fine as well. Only when it's forced to expand, okay, then this will happen. Okay, your school wouldn't go into detail on how expansion of octet works, but I feel that it's very, very good to understand this because you can apply it for sulfur, you can apply it for chlorine or whatever. Okay, now the easy trick is this, guys. Okay, phosphorus has 5 valence, right? 5 valence, you just need to multiply by 2 to get 10 maximum electrons. Similar idea if I change this to sulfur. Sulfur is 60, then so this is 3p4, right? Now how does 3p4 look like? 3s2, 3p4 looks like this, correct? Now how many people want to move out now for their own room, basically? 2. Now this guy can move over here, but this guy can also move over here. They're all single. So how many unpaired electrons are there? How many unpaired in total? 6. 6 unpaired electrons means he can form 6 bonds. So sulfur can hold a total of 12 electrons. So you can do the same thing, basically. You can try yourself for sulfur, for chlorine, you'll notice it's just a pattern. Okay? So in other words, let me just stick to phosphorus for this case. So the reason why electrons can jump, can someone just possibly tell me once again? Why can an electron just simply jump to the 3 orbitals? Why is that possible? Why is the electron over here able to jump to 3D? It's because they are energetically accessible, right? It means that the energy levels are so close to one another that an electron can just jump to the other one very easily. Compared to, let's say, guys, is it possible for a 1s electron to jump to, like, let's say 3s? Not possible, right? Because they have such a large energy gap, so it's definitely possible over there. So that's what energetically accessible means. All you need to write in exam, just this sentence, and then you get your answer. You can justify why they can expand their octet. Any questions so far? Okay, so if you don't have, right? So that idea over there is basically your. Okay, what do we have? Okay, the expansion of octet. Okay, we'll talk about one more example first, and then we can try a little bit of more questions. Okay, so guys, there's this one example that's not that important. Okay, as I mentioned, guys, you don't actually need to have 8 valence electrons, as mentioned. Radicals are one example. Expanded octets, another example. The last one is not that important because there are electrons which can hold less than 8 valence electrons. As we have mentioned earlier, we have VF3. Now the reason behind that is because boron has 3 valence electrons, so it can hold up to a maximum of 6 electrons in its valence shell. Okay, let me show you guys some examples, right, that will usually have less than 8. Okay, so VF3 is one of them. Another one will be AlCl3. Aluminium is also in group 13, so 3 valence, you can hold a maximum of up to 6 electrons. Okay, some of you will tell me, right, this is an ionic compound, but actually in JC, this is a covalent compound. And I'll explain why in the next lesson. Okay, a new concept. Another one will be beryllium. As you all have noticed, beryllium is a metal. It's in group 2. Beryllium has 2 valence electrons, right? How come it can undergo covalent bonding? Okay, never mind, I'll explain that eventually. But it can only hold up to a maximum of 4. Not that it has a choice, okay? It doesn't have a choice to hit 8 valence, so that's it. Okay, so try to note these 3 examples, very common examples, usually involving boron, aluminium, or all right. Okay, I know just now I say I don't really touch into group 2 or group 13 or group 1 because they are metals. Metals usually undergo ionic bonding, but they undergo covalent bonding. And that's explained in a new chapter, basically next lesson. Okay, any questions so far? Okay, do you guys need a break first before we look at even more practices? Okay, perhaps we take a 5-minute break first. Okay, 5-minute break because later there's a lot of examples. Okay. Okay, so take 5-minute break, go to the toilet or whatever. Okay, then we can continue a bit. I need to refill my bottle as well. Your two friends' names are what? Heidi and come back to this. Okay, come. Okay, then we're going to spend the rest of the time, basically the next half an hour, going through a bunch of examples. I'll also add on other examples if need be. Okay, basically by the end of this lesson, as I've already mentioned, by the next half an hour, you should be very used to the idea of dot and cross diagrams. So on page 27, you will see basically a combination of everything that we've covered so far in all those examples. So we're going to split it into a couple of parts, right? Okay, I need you guys to take a look at parts 1 to 3 first. Okay, so we do bit by bit, okay, so that it doesn't get too much. Okay, so we even did part 2 already actually. So just possibly try that again. Okay, maybe you can try the first 4 parts first. Carbon monoxide is a bit tricky, right? If you can't do carbon monoxide, never mind, you can move on to the rest first. we've done NO2 just now. Right, the first four, and then I will talk about a few things. You guys can also include CLO in this page as well, because something I want to discuss, CLO. We have nitrogen is not really true. Security, which means you cannot go more than 2. Okay, so I want to discuss the first four parts because there's a little bit of a revision that I want to do for the fourth criteria. Okay, so anyways, let me just erase this again. We will write a new and improved version of this. Okay, but anyways, okay, I will skip carbon monoxide first. Nitrogen dioxide has a dative bond because nitrogen cannot hold more than 8. Okay, some of you will have gotten 9 electrons, must change it to a dative bond. The center give to the side. Okay, that's the answer. Okay. For NO, all right, NO once again is one of those 2 atom kind of situation. So you have no idea whether to form double bonds or triple bonds or whatnot. Okay, take a look at this. Our oxygen here can form how many bonds? 2 bonds, right? Our nitrogen can form 3 bonds. Logically speaking, which one will you try? Triple or double? You will try the double bond, right? Because triple bond is a little bit too much for oxygen. Let's try not to go ahead of any one of their maximums. Oxygen try to hold a double bond, so let's just do something like this first. Okay, is there anything else that we need to fill in? Oxygen is quite straightforward. Nitrogen, how many more to fill in? Okay, 3 more, right? So the 3 more means the lone electron is on nitrogen. Now, does that make sense? Yes, because this is where I need you guys to check whether it's a radical. Here's a total of 11 valence electrons, 5 plus 6. So that's how you know there is a lone electron. And guys, where must the lone electron be located at? On oxygen or on nitrogen? It must be on nitrogen, right? Because nitrogen has the odd number of valence electrons. So it cannot be on oxygen. Now, why am I bringing this up again? Is because I want you guys to go back to ClO. In order to draw ClO, we have to just place something like this, correct? Now, how many bonds can oxygen form? 2. How many does chlorine form? Now, generally, chlorine can form 1 bond, right? Okay, so let's see. Just now, I immediately try a double bond, but some of you guys might try a single bond because chlorine can form 1 bond, oxygen can form 2. So we just try not to exceed the maximum of chlorine. Correct? So chlorine 1 bond will look something like this. So 1, 2, 3, 4, 5, 6. But oxygen, how many more do I need to fill up? 5 more. 1, 2, 3, 4, 5. Now, as we have already established, this guy has 13 valence electrons, which is an odd number, which means there is an unpaired electron. Agree? But where is this unpaired electron? Currently, with this configuration, it's on oxygen. But is that allowed? Oxygen is the one with even number of electrons, right? The odd number is chlorine, so it should be on chlorine instead. Does that make sense? So, what's the correct answer here? Because I hope you all know this. Chlorine is in period 3, so it doesn't just have to form 1 bond. It can form more than that actually. So that's why, right, just now, even though this is not, okay, it's not correct, the correct answer, we can try forming a double bond for ClO instead. A double bond will look something like this. Oxygen, you fill up everything else. Chlorine, how many more do you need to fill up? Chlorine has 7, so we need to fill 5 more. And as you can see, this makes more sense because chlorine can hold more than 8 valence electrons. And at the same time, the lone electron is on chlorine, which has an odd number of 7 valence electrons. So this makes more sense. Compared to the other one just now, you can get the point out of it. You can write down the errors for this. Okay. The error that we have faced over here is that oxygen has the lone electron, which is not correct because oxygen has 6 valence electrons. You shouldn't have the lone electron on oxygen. Does this make sense? So ClO is a little bit of a special case where we can consider a lot of different things together. So that's why I need you all to include ClO as well. Okay, so far? Cannot. So let's move on from oxygen. Okay, or ClO, my bad. Okay, let's look at SO3. Guys, how many bonds can oxygen form? Double bond, right? So double bond immediately for all the 3 oxygens. Now, do we need to change anything here? Do we need to fill up the central atom? The sulfur has 6 valence, and all the 6 valence has been drawn. Agree? Are we done here? Yes, we are done. Okay, we do not need to change this to dative bonding. Why? Sulfur has more than 8 electrons, and it can hold more than 8 electrons. And this is where I need you guys to revise the fourth step basically. If the central atom can hold more than 8 valence electrons, you leave your answer. You leave your answer. But if the central atom cannot hold more than 8 valence electrons, because it's not in 3, then I need you guys to change it up to dative bonding, in which the central atom gives to the side. Now, from this, right, I hope you guys have noticed that dative bonding is your last resort. In other words, you cannot go into a question expecting yourself to do dative bonds. Dative bond only comes in to troubleshoot your answer, to fix your answer, when you only realize it cannot hold more than 8 electrons. So I cannot have a double bond, I cannot have a dative bond then immediately. Okay? In other words, guys, SO3 has 12 electrons, it is correct. It can hold more than 8. Leave it. Do not change it to dative bonds. This is the same idea as SO2 that I talked about earlier. Okay, so I introduced SO2 earlier. You guys did something like this. You guys did a dative bond because you were not aware that sulfur can expand its octet. Now, even though this is very nice, oxygen has 8, sulfur has 8, oxygen also has 8. This is not correct because we need dative bond. Once again, dative bond is a last resort. I say again, dative bond should be a last resort. The one that's before that, right, is sulfur that can hold more than 8. Since sulfur can hold more than 8, there is a preferred structure. And the preferred structure is this. Sulfur forming 2 double bonds with both oxygens. So this is the preferred answer. Because sulfur can expand octet. So yes, I mentioned all this just now, you might be a bit confused. Okay, but now let's finalize it. That's the idea. Okay, you can expand your octet, so this comes first. This makes your life a lot easier actually. Okay, you might think this is a bit confusing. But whenever you can expand your octet, right, it saves you a lot of time. You don't have to erase, you don't have to change the dative bonds. So that's the beautiful thing about this. Okay? Any questions so far? Anything else you want me to consider? If there's nothing else, right, I'm pretty sure I can leave it to you guys to try the next couple of examples to finish this up. Okay, so let me erase some. Oh, we haven't gone through CO yet, okay, I haven't gone through carbon monoxide. Okay, let's go through this and then I'll leave the rest up to you guys. Okay. Okay, guys, take a look. How do we use CO? Carbon can form how many bonds? 4 bonds, oxygen can form 2. So ideally, which one should we choose? 2 or 4? Okay, obviously 2 bonds lah. Okay, choose the minimum. In this case, we have a double bond here. You fill up oxygen. So oxygen now has 8 valence. Carbon, how many more do I need to fill up? 2 more, right? So carbon has 4 valence, 2 of which never used for anything. Now the thing with this is that carbon has how many valence? Total now. 6. Now I did acknowledge that yes, it is possible to have less than 8, right? But guys, this is not the best answer. Even though this one doesn't violate any criteria, there's a better answer you can do this. There is a way to make both of them achieve octet. How? We brainstorm together. How? What can we do? Okay. Do you all notice, right? Okay, that there are so many lone pairs. What that means is that there are so many electrons just sitting at the side doing nothing. What can we do? What can we do for what? For oh, 4 in the center. Okay, that's a bit much. Okay, you all realize there's so many bystanders doing nothing. We can make them do something, right? So what can they be used for? The idea of just taking and just giving dative bonds. So guys, what's gonna happen is this, there's nothing wrong at the moment, right? We can make it better. There's nothing wrong, just make it better, so there's no need to erase. I'm just gonna take whose electrons? Oxygen's lone pair and put it in the bond. Basically, it's now up for sharing. Let me move this down to make it nicer. Does this make it 8 electrons? Can you all see that? Carbon has 8 in total, 6 up for sharing, 2 for himself. Total 8. Oxygen also the same thing. It's tricky, I know. That's why I mentioned already. A carbon monoxide is another tricky one. I need you all to put a star next to it. Alright? In other words, guys, how carbon monoxide looks like in real life is this. Remember, a dating bond is an arrow pointing from oxygen to carbon, not the other way around. So it's a triple bond. Carbon monoxide is a triple bond from now on. You must know this. Okay? They have tested carbon monoxide before. In future topics, if you don't know that carbon monoxide is a triple bond, you will get questions wrong. Alright? It's not technically a triple bond, it's like a double bond with a dating, but still considered triple. All okay so far. Alright? So it's all about using the lone pairs for something useful. Now the lone pair is no longer a lone pair, it's now a bond pair. It's useful. Okay, Ken? Right. Okay, so not much time left, and you guys will try the rest. Six, 7, 8. Okay. Interesting factors. Yeah. Okay, so you all notice how about a noble gas on Earth, right? The noble gas you all have been taught cannot undergo bonding because they have already have 8 electrons, right? So that's what you've been taught, okay, but that it can undergo bonding as well for a very specific reason, right? Any guesses? Why is it that xenon and noble gases in general can also undergo covalent bonding? You all have been taught that it's very unreactive because it already produced octet. But guys, again, this is what you've been taught in secondary school. Right now, is 8 electrons the maximum? But the thing is, right? Oh no, it's okay. It's correct. It looks weird only, but it's still correct. Okay, it can undergo covalent bonding because it can expand its octet as well. Xenon is in like period 3 or 4, right? Okay, so definitely can expand its octet. Yeah, I know it looks weird, right? As long as it looks. That's okay. That's a solution. It just looks weird. But no, just trust whatever. You have a lot of this feeling in exam, like you will see there's something that doesn't feel right, but it's actually right. Okay? The reason why you feel this way is because you just never see before, so you just need to keep going. Okay, let me draw the answer for SO42 minus. Not a difficult question, because sulfur can expand its octet. I do not want to see any negative bonds in SO42 minus. Okay, remember the 2 minus means 2 oxygens have 7 valence. They can only form 1 bond. 1 bond, 1 bond, because these are the additional electrons. The other two oxygens are normal, so they just form double bonds. Sulfur in the middle has 12 electrons, and that's okay. Leave it. So much better, right? Okay. How about XeF2? Okay, so XeF2, you just see it surrounds xenon with 2 fluorines. How many bonds can fluorine form? Fluorine can only form a single bond, so just stick to that first. But how many other lone pairs are there on xenon? How many electrons are not involved in bonding? 6, right? Okay, because 8 valence, so 6 more. 6 is in the form of how many lone pairs? 3 lone pairs. So all you need to do here, right? Just take, okay, you can put 2 on top and 1 below. Like that. Okay. What do you mean? Oh, 3, guys. It's a pair. Not a triplet. It's not a triplet, huh? Okay, okay. I appreciate the thought. I never thought about that as well. No such thing as lone triplet. This is not lone pair. 3 lone pairs. It's possible, guys. Now, guys, this is actually a good way for me to tell you guys what's coming up in the next lesson as well. Okay, next lesson, you will see that there are compounds with 3 lone pairs as well, and you'll be responsible for the shapes of the structures. I won't tell you any about that yet. Okay, as I mentioned at the start of the lesson, today dot and cross is only half of the entire thing. The next lesson is another half when we talk about CPR theory. That one a little bit more challenging already. Okay, that's why dot and cross must be. Okay, so far, any issues with this? Okay, have you tried part? What the hell is this number? Part 7. Have you tried it?
Is it the
N2O. If you haven't yet, we can discuss one idea. Because N2O is another tricky one, but which I'll need you guys to start. Okay, right, guys. N2O is another question they love to test, especially RI. Love to test this. Because it's a big deal. Okay, so guys, can you just first tell me, we discussed part 7 together. How will you arrange the electrons by the how will you arrange the atoms, by the way? What's the arrangement? Who's in the center? Okay, some of you will say O, so it's very nicely symmetrical, right? N-O-N. Well, it's because usually we like to 6 symmetry, right? This is wrong. Why? Come back to the basics. Guys, how many bonds does oxygen form? 2. How many bonds does nitrogen form? Not 5. Nitrogen can form 3 bonds. Based on the first principle, nitrogen should already be in the center, correct? If you're still not convinced, let's look at the second one. Who's the less electronegative atom? N or O? Both principles are pointing to the fact that nitrogen is in the center. So it should be N and O. Now, the reason why they love testing this is because of this arrangement. Now, some questions are, if they are nice, they will tell you who's the central atom. But I've only seen that once. I think they will really in a good mood that day. Okay, but usually they don't say this. They just leave you to die. Okay, so please remember, N2O is very special. They can test this. If they were to test one dot and cross, I will honestly say it's N2O. Okay, give this a try. Right? Okay, from here you can follow whatever I taught you guys, right? You definitely can draw the chart. Okay, just a heads up, there are 2 possible answers for N2O. Some of you guys might get the other answer, some of you guys might get the more normal answer. Doesn't matter, right? Okay, so the thing is, it is what you have done first. Okay, guys, let's go through N2O very quickly. N can form how many bonds? 3 bonds, right? Look at the side angles first. Okay, triple bond is here. Double bond is here, right? So just fill in everything first. Like this. Okay, but what's the problem with this structure? Yes, nitrogen has all the 5 valence, but now it has 10 valence in total. That's not allowed, right? So there are 2 fixes to this problem. Okay, so let me go over my preferred method. You can either remove the triple bond because it's too much, or you can remove the double bond. Okay, so I will remove the double bond, and now you take a look, guys. You have to do dative bond where your center gives to the side, right? The center, nitrogen, has another 2 more electrons. Just give it to the side. Oxygen has 6 electrons here that are not used in bonding. This is one solution. Basically, how this looks like, N triple bond, and then a dative bond like this. Now, there's another solution here, which is, instead of removing the double bond, so I leave the double bond here, I can choose to remove the triple bond instead. Okay, guys, let's work this out together. If you remove the triple bond, there has to be one dative bond, right? We mentioned that's the solution. So the dative bond is from the center give to the side. So there's 2 electrons like this. How many other electrons are there on nitrogen that I need to go in? The center one. I left with 1 more, right? Now this 1 more can actually just be a normal covalent bond. In other words, nitrogen here has how many more to fill up? 4 more, which is perfect. So in other words, how this looks like is a nitrogen with a dative and a normal bond, and then a double bond on the other side. There are 2 answers to this. Whichever you prefer. Oops. I would prefer the one on top because I feel it's easier to determine. The one at the bottom has what is a mix of dative and single bond, which I don't really not a fan of this. Yeah, but based on what I taught you guys, this also viable, very, very viable. Okay. You put one dative bond, then you realize that actually all the numbers match up. Alright. Okay, so very quickly finish up ClO3 minus and we're done for today. Right? Very normal structure, ClO3 minus. Nothing special about this guy. I keep mentioning that they will just test 1 or 2 dot and cross diagrams in the exam, but that's not entirely true. Because we still haven't looked at the next part of dot and cross yet. That's why we're doing so much of this today. It's because of that next segment, right? That's why we need to do so much dot and cross. Cl must be less, not oxygen. Because Cl is less electronegative than oxygen. I think the top 3 are FON. So definitely Cl is less. And Cl can expand the octet. Anything that can expand the octet, right, usually is in the center because it can take in as much as it can. Okay, I'll go through in another minute. Right, okay, let's go over the answer here. The negative charge means to do what? You must add an electron to the oxygen. Okay, so oxygen is more electronegative, give it to E. He has 7 valence, so he forms a bond. The other two oxygens will just form a double bond each. Is this too many electrons for the center? No, right? Because fluorine is in period 3, he can take in as much as he can. Is there anything else I'm missing? Always go back to the center and make sure he is correct. Chlorine has 7 valence, currently only 5 is used in bonding, so another 2 extra. That's your lone pair. That's ClO3 minus. Any issues with that? Okay, so that's pretty much all we have for today. If any questions, you can ask me. Okay, but the next page you can see there are 2 questions, right? That's very, very insignificant. Okay, we talked about that before. Okay, maybe the third question, I'll just briefly talk about it the next lesson. Okay, but eventually we're gonna learn it anyway. Okay, so yeah, dot and cross for this entire lesson, because next lesson we are still gonna draw dot and cross, but it's expanded with this theory. Basically, we're gonna convert it into the 9 structures. And that was not as easy as it seems. Okay? So yeah, any issues? Any questions? Okay, don't have, yeah, that's it for today. I will see you guys on Sunday. Okay, we will not just be doing VSEPR, we are also gonna do small little concepts here and there. Touch a little bit more about electronegativity and all that.